both. They're not that bad. They're really not that bad. Okay, so first off, if you read a problem that says anything about the word titration, it's not a buffer, probably. Probably. It's a titration. Okay, in a titration, we take an unknown liquid. And I honestly think we did this already. So we don't know the concentration of this acid. That is unknown. But we do know something. What we know is that at a pH of 7, the H plus concentration is equal to the OH minus concentration. Like we know that. So if I don't know this, but I can add this until I reach a pH of 7, it will tell me that what that was. You with me? So if we're at a party and I don't know how many like boys are in there, I can send in 20 girls and I say, all right, find a girl to hang out with or find a boy. I don't remember how I started the story already. And then if you can't find one, come back out. And if 3 of them come back out, then how many were in there? 17. Okay, it's not, I know that's a weird analogy, but it's not that hard to figure out. Okay, so once again, what we don't know is the concentration of this acid, but we will know the volume. Because we can just measure that with a beaker or a graduated cylinder, right? Okay, now what I do is I take a base or OH minus and I add it to this solution until I reach a pH of 7. Of this base, I will know the concentration. I know its molarity. All right, so let's just do an example. Let's pretend here that I have 50 milliliters of my acid. Okay, good enough, H plus. All right, but I don't know the concentration. So what I need to do, I have 2 molar NaOH here. And I'm going to open this valve and I'm going to add, let's say, I don't know, 21 milliliters. And once I get 21, I'm keeping track of this. Once I added 21, it turned to 7. You okay with that? Okay, so I know now on my base side that 2 molar times 21 milliliters is equal to some concentration that I don't know. This one, it doesn't matter, and I'll show you why in a minute. But yes, you can, but you don't have to on this one. And the reason why is because both units here are in milliliters. So they'll cancel each other out. Okay, so 2 times 21 equals X times 50. Well, what math do we have to do that? We take this, and it's 42, and we divide it by 50. And that would tell me I have 0.81 molar. Is that wrong? 0.84 molar. Oh yeah, why did I cut in half? I mean to double it. And that's literally all I would do. It's not awful, right? Okay, it will get more complicated now. This is we're assuming they're a strong acid and strong base. When it is not, it gets a little bit trickier. We'll be all right. All right, here we go. All right, this is just more stuff. We're going to support what I just said. A pH meter, that's what we used in the previous one. That's this thing right here. That's used, or more commonly, an indicator is used. And did we do one of these? Okay, I thought we did. So we added bromothymol blue, and I don't remember if it was acid or a base. Was it vinegar or aspirin? Do you remember? Vinegar. Okay, so we added it and it turned yellow, and then we added bromothymol blue until it turned green, and we kept track of all the stuff, and we were able to pretty much discover what that was. Okay, so they're used to track the pH of the solution, because once again, at 7, we know we have stoichiometric amounts of acid that are equal to that of the base. Now, that's a super complicated way to say it. Stoichiometric amount. Why it's put that way is because if you add like a diprotic acid, you're not going to get them that they're exactly equal, because this gave 2 H's to every 1 OH. So we would have to possibly apply that. So that's why it doesn't say it's always equal. It just says stoichiometrically equal, which accounts for the coefficients out in front. All right, so these are fairly standard titration problems. So it says a 20 milliliter sample of 0.2 molar HBr is titrated with 0.2 mol NaOH. Calculate the pH of the solution after the following volumes of base have been added. Okay, so the first one is 15 milliliters. All right, so we look here and we have 20 milliliters of 0.2 molar, and it is titrated with 20 milliliters, or sorry, 0.2 molar NaOH. Then we're going to look at the volume. So the equation for titration says that the volume of the acid times the concentration of the acid is equal to the volume of the base times the concentration of the base. You okay with that? All right, now in chapter 4, we did these, but we didn't take the next step, which was to find the pH values. And so here we are now. So we have the volume of the acid is, I'm going to stick with 20 milliliters. And that's because if both sides are in milliliters, then I don't have to convert them. All right, times the concentration of this is 0.2. Those are my values for the acid, right? And then they will equal, I'm adding 15 milliliters of my base. Whoops, I just did it myself. But do I know the concentration of the base? This time I do, right? It's what? 15. So I should have read this better, because this isn't titration math. You're welcome for me being amazing. What's that? It was 15 milliliters right here, and it said, oh, it's not. I'm just sucking. It is also 0.2.
Yeah, so you're actually lying to us.
I've lied to you twice now. Yeah, it's because this isn't a titration problem. You're welcome. It is, but I'm an idiot. So just shut up. Well, I'm confused clearly, right? Okay, well, I thought we were going to do a titration because I didn't read it careful and then do the pH, but instead we're just going straight to pH. So I apologize. Is this going to be a buffer? No, it's a titration. I look and I have HBr, which is considered a what? Strong acid. I'm sorry, I screwed up. I just should have read the whole problem first. It's a strong acid. And what is this? Strong base. So this is simply a neutralization reaction. All I have to do here, which we have already done before, is figure out which one I have excess in. I'm sorry, I should have paid attention. So we are going to convert to liters. 0.02 liters times 0.2 equals, and that's moles of, oh my laws, could I screw up less today? We'll see. That's moles of what? All right, HBr or H plus. So far, okay? I'm pretty good at this. Oh, I'm ready now. Okay, then I have 0.015. Is that correct? All right, and I'm going to multiply it by 0.2, and it is that many moles of OH minus. Did I screw up that step yet? Okay, I feel okay then. You what? To find moles, you take volume times molarity. Okay, what did I have here? I have excess of which one? All right, I have 0.001 moles H plus in excess, correct? Now, I don't form a weak acid here because I don't have the conjugate base of a weak acid. I don't have the conjugate acid of a weak base. So this is strong acid, strong base. So I just find which is in excess. Now, this word says moles, but for pH, I need to take concentration, correct? Okay, so I divide this by the total volume in this problem, which would have been okay. And what is that number? And that is the H plus concentration, right? So I'm gonna take the negative log of this number. 1.5 what? All right. All right, I am sorry I didn't read that problem well enough till we had already started a couple lines of notes. Okay, now you got to do it 4 more times. Okay. Wow. These two girls got a drink at the exact same moment. It was art. Okay, we're going to do the exact same thing. Will you try number B on your own? Letter B, I mean, not number. Letter B on your very own. Give that a shot for a couple minutes. I'm going to pause, make sure I unpause. I recorded most of it, just not the end. Okay, it doesn't want to go back anyway. Nothing wants to work today. Okay, unlike in previous cases, the conjugate base of the acid now, when we have a weak acid and a strong base, affects the pH when it's formed. Why? All right, so the example here they have HC2H3O2, and I neutralize it with OH minus. All right, and that kicks off the H to make water, and C2H3O2 minus. And this is the conjugate base of a weak acid. So if any of the water breaks apart, which water does at equilibrium, not very much, but some of it does, then it will bond back with this to make weak acid. So we have a neutralization reaction, but as part of that, we're left over with a conjugate base of a weak acid, which will affect the pH. Yeah, it depends on how much extra, and it depends on the Ka. All right, now, this isn't super hard. The pH at equilibrium will be greater than 7. Now, this actually logically sort of will make sense if you just think about it. Which of the two of these is the word strong associated with? Base. So the pH at equilibrium would be more basic than it would be acidic. So if you have a weak acid and strong base, you simply have to know, you don't have to do a ton of math here. You just need to know that the equivalence point now is like 8.5 instead of 7.0. Are you okay with that? So add base, it becomes more basic. Then go ahead.
So it's like the equivalence point is when like the H plus and the OH are neutralize each other, but then because it's the conjugate base, when it breaks and like separates those stuff, that makes it.
Right. Exactly.
When you add
Acetate.
the conjugate base of a weak acid to a solution, it makes the solution more basic.
Yeah.
Okay.
Yeah. So I can have just pure water, put not anything we consider an acid or a base in, but I can change its pH. So I could put acetic acid in there, just solid, or sodium acetate, sorry, solid sodium acetate, and that would make it more basic because the acetate will remove an H to become the weak acid.
And so even though it's forming an acid, the solution becomes more basic.
Yep.
Yeah.
Because by forming an acid, it caused the H plus concentration to go down. It's very weird. You're like, wait, I made an acid and it made the solution basic? Yeah.
Saying it sounds really weird, but like when you think about like adding the conjugate base, it's like, well, yeah, it's going to become more basic.
By forming an acid.
Yeah, which doesn't make sense. Oh, we just ignore that part.
Yeah. It's, I don't know. I find it kind of interesting. But hopefully this isn't that bad. Whatever the strong one is, that's the side of 7 you'll be on. Okay. Phenolphthalein is commonly used as an indicator in these titrations because its range of change is above 7. Okay, universal indicator, it changes colors all through, but most indicators only change color in a specific range. And there's like a huge, I mean, there's thousands of them in charts like at college. You'll see it'll be the smallest font ever, and it just looks like a rainbow that kind of like goes sideways and then it comes back. There's one in your book that you'll never look at because you don't have a book, but there's one in the online book that you haven't clicked on that link in 6 years. But I bet there's one here actually. What am I doing? Okay, Tom, there ain't none. I grew up in Vernal. All right, well, anyway, are we sort of all right with that? You don't have to know this, but what you do need, like the phenolphthalein part, what you do need to know is it's going to be a multiple choice question if you have it on the AP test. And that question would say, like, we're doing a pH with these two things, or sorry, titration with these two substances. Which indicator below would be the best one to use? And it would say phenolphthalein with a range of 7 to 8. It'd say bromthiamyl blue with a 6.5 to a 7.5 or whatever. And you just say, hey, it's got to be the one that's around 8 or something like that. Like it'll be pretty specific. All right. So same example here. At each point below the equivalence point. So before, like, whoops, I'm doing it wrong. It comes along here, it creeps up, and then it gets vertical, and then it gets like this.
Before it becomes 7.
Right. Now, a strong acid, strong base looks just like this, like flat, vertical, flat. You can tell it's weak in a picture of the graph if it's more slow rise, vertical, slow rise. They're much more angular. All right, anyway, at the point below the equivalence point, So like right here. The pH of the solution during titration is determined from the amount of the acid and its conjugate base present at that particular time. All right, that sounds like a ton of fun. So here we go. A 50 milliliter sample of 0.1 molar HF is titrated with 0.1 molar NaOH. What is the pH after the addition of the following volumes and bases? So this is really similar to what we did before, but slightly different. All right, so I have a weak acid right here, right? We okay with that? All right, and then I'm adding a strong base. So let's look at what I have here. I have 0.05 milliliters times 0.1 molar HF. So what do I end up? What did I do wrong? Liters. Thank you. What do I end up with? 0.005 of what? Moles of HF. So that's weak acid, right? Okay. Then I have 0.1 molar NaOH. So that is 0.1 molar NaOH. And I'm taking 0.04. Yeah, from right here. The 0.04 came from here. So what do I have left now? 0.004 moles of what? NaOH. Okay, so I'm just going to say OH minus. Are you right with that? Okay, what will the NaOH or the OH minus do to the HF? It neutralizes it, correct? All right, so left at the end, do I have any extra HF? I have how much? 0.001 or 0.0001? And that would be moles of what left? And then how many moles do I have of F minus? How do I find the pH of a solution that has a weak acid, whoops, and its conjugate base? Henderson, Hasselbalch. Yeah, it gave it to us right here. What? Of F minus? It's the amount that was liberated from here as OH took the H.
Unless it's a question you just made up, is the Ka for HF always going to be that?
Unless it's one I made up, yes. I may have looked it up. I have no idea. Hey Siri, what's the Ka for hydrofluoric acid?
Here's what I found.
What does it say?
It doesn't know what I meant. It just took me to the Wikipedia page.
That's very helpful when it comes to
Just stupid, huh? All right. So whatever, we take the negative log of 1.8 times 10 to the negative 4. And do we add or subtract? Add, because David Hasselhoff's a happy man, right? He's also a bad A, isn't he? So base is, acid is, what's that? Still didn't hear you. What?
4.35.
Okay. 4.35. This is a problem I typed. So yeah, there'd only be one technically, but the AP test won't do that to you. They'll give you 3 or 4. All right. So right here, below the equivalence point, should it be acidic? Yeah, it was an acid that I'm adding base to. Before it's equal, it should be a number under 7, and it was. It wasn't it's not super acidic because, whoa, my knee, that was weird. It's not real acidic because I have a weak acid, right? So this is a reasonable answer to my pH problem. All right, at 50, what are we going to have at 50 milliliters? Is the equivalence point at 7? No, because we have a weak acid and a strong base.
So you would have to do
So at equivalence point, I'm not making water, I'm making an amount of weak acid and then the conjugate base. The acid's gone now. I just have the conjugate base. So follow me here. No, Tom, wait a minute. Wait a minute. I'm doing something wrong in my head. Well, let's just math it and see if I can figure out what I'm thinking wrong in my head while we're at it. So we have 50, we had 0.00 what again? Of HF, and we have 0.005 of OH minus. So how much HF do I have? 0. How much conjugate base do I have? I do, and it's just conjugate base. I've literally forgotten.
Go, Jared! I love you, Jared.
Thank you. No, that did not help me remember. I don't remember.
Isn't it Ka equals X squared over?
No, there's no acid. I have to remember it.
You just do it for a base and then. Wouldn't it be 14?
No. No. Why am I being an idiot right here? I know, because I haven't done it in a year.
No, it's just a weak acid. So we do the.
But there's no acid. The acid was completely dry. So I'll remember. If I don't, I'll read it on my prep hour and we'll get it. Okay, so part C. What do we have now? Extra what? Extra base. And is this a weak base we're making? No. So in part C, I don't care about the weak acid or the conjugate base. I simply care about the excess OH minus. So we had 0.005 HF, right? We have 0.006 of OH minus, correct? All right, so what's in excess? 0.001 of OH minus. That's the moles, but I need its concentration now, right? So I divide that by the total, which was 50 plus 60, which is 0.11. And I end up with I did it. It's okay. And I'm going to go ahead and put this right here. I'm going to say 14 minus. Why am I doing that? Because the excess is a base. All right, what did this number right here equal? 0.009. Okay, now this is the concentration of OH minus, right? So I take the negative log of 0.009 and subtract it from 14. $11.958 sounds pretty close. Yeah, you're welcome. That's okay. Okay, besides the fact that I don't remember the math on that one, those two weren't that bad, right? So under it, it's a buffer. Above it, it's an excess. Okay. Yeah, I'll remember this. I'm annoyed at myself, but we'll get it. Good. All right. You don't have to like know any of these. You just kind of need to know this idea. With weaker acid, the initial pH is higher, and pH changes near the equivalence point are more subtle. So you could have a multiple choice question now that asks about like this. Yeah, well, it says something like the green line is most likely which of the acids. And it wouldn't give you the Kas here. It would be the Ka here. And it would give you like 1, 2, 3, 4 for A, B, C, D. And it wouldn't be like most likely the top one or the bottom one, because those would be the strongs. So you would say, all right, if it's higher and flatter, you choose the smallest Ka. If it was lower and more steep, you choose the bigger Ka. Like, I don't know. They're not a common question. Oops, I didn't mean to do that. Okay, a weak base with a strong acid. Everything's the same, just the reverse. So the pH at the equivalence point in these titrations is less than 7. And that makes sense again. The stronger thing, which is the acid, makes the pH, like that's where we end up on the pH scale. So if it's strong acid, I'm going to end up on the acid side of the scale, not the base. And methyl red, once again, you don't have to have that memorized, but methyl red is a good indicator choice for a weak base with a strong acid. All right, so far, sort of okay? Okay. Now, before you panic, you need to know extremely little about this chart. All you need to know is if you see a titration curve with multiple curves, it's a polyprotic acid. Yeah, you like how auto-corrected? That was cute of it. Why did it do that? I'll be more dramatic and see what happens. There we go. So there's literally no math on these that we do. They're too complicated. You just have to know if it has multiple steps, it is a polyprotic acid. Now, it could be the other way. And then you just say it's polybasic. You okay with that? It says in these cases, there is an equivalent point for each dissociation. You don't have to know them. You just need to know that, oh, that's a weird looking curve. That must be the titration of a polyprotic acid or polybasic base. Okay. I would definitely draw these in your notes unless you already have. The AP test loves pictures. All right. So EQP means the equivalent point is at 7 pH. SA means strong acid. SB means strong base. This is an errant mark. I apologize. It's not been my best day. What's that? It's been good. All right, I'm going to stop my video so I can get going.